Hello, everybody, and welcome to the first event of the Codex live event. Together with me, I have Stefan.
Hey all, good
Hi.
afternoon, morning, evening to everyone.
So together we're going to show you our brand new training called SSCH, Solidity Smart Contract Hacking. I'm going to bring on stage the slides. But before we deep dive into the topic, I just want to give a brief introduction about me, and Stefan will do the same for himself. So I'm Davide Cioccia. I'm the founder of the Codex, cybersecurity company focusing on DevSecOps and security development. I like to contribute to the security communities, so I'm OWASP member and also DevSecOn chapter leader for the Netherlands. And during my free time, I like to play tennis and padel. Who doesn't these days? Stefan.
Hey everyone, thanks for joining. I'm Stefan. I'm also part of the Codex as a senior security consultant. Besides that, I'm a proud member of Zero Science Lab. Has been in cybersecurity for a while now as a pen tester, a security engineer, and I do love doing security research. Like Davide, sometimes also together. We did speak to various cybersecurity conferences. Some of you we might met. For the others, hopefully in the upcoming ones, or the ones that will follow. Now that sort of the physical conferences are coming back, looking forward to meet you.
Hopefully soon. Hopefully soon. So what is Decode? Is just a few words about us. As Stefan said, we love to speak at conferences, and we try to do that as much as possible. We talked at OWASP, Black Hat, and DevSecOn. And we are a group of security engineers with 10 plus years of experience working in different categories like IoT, banking, fintech, e-commerce, and focusing on application security and DevSecOps. But what about today? So the agenda is split in two. We have first part of the webinar will focus on hacking smart contracts. We will go through a brief history of Ethereum, the Ethereum virtual machine, and Solidity. And the second part is related to famous hacks, the DAO hack. And we will see also an example of the reentrancy vulnerability that was exploited during this attack. And in the second part, we will go through the content of the training, what's in it, how to join the course, and don't leave because we're going to share a coupon code that you can use for the first session of the training that is scheduled for end of June. So the hacking smart contracts, as I said, we're going to go through a brief history of Ethereum, a few details about the Ethereum virtual machine, and then deep dive in Solidity, in smart contracts written in Solidity. So if we look at this timeline, everything started in 2013 for Ethereum when the first white paper was published. In 2014, the first official Ether sales started. And from 2015, the hard forks started till 2021. We'll see more in 2022, I guess. In 2015, the Frontier hard forks introduced a gas limit for blocks of 5,000 gas, but then that was removed directly in the next hard fork in the Frontier towing. And in 2016, we already named it. There was the DAO fork, and the DAO fork was in response to the 2016 DAO attack, where an insecure DAO contract was drained for over 3.6 million Ethereum in a hack. I think today those 3.6 million are worth maybe 9 billion, something like that. And the fork moved the funds from the faulty contract to a new contract that had only one function, the withdraw function. We'll see later also how this was written. In 2016, the hard fork Spurious Dragon was introduced to respond to the denial of service attack and to replay attack, so introduce some protection against replay attacks. And the coming forks introduce improved scalability, reduce the costs, till 2020 when the Beacon chain Genesis was introduced. And this is the very first tentative to move to Ethereum 2. It introduced proof of stake. Some of you might know this hard fork as phase 0 or block 1. So what's special about block one and the big on-chain Genesis in Ethereum? Well, the big on-chain Genesis is the first step towards Ethereum 2. It wants to introduce many improvements. First of all, scalability. So with this fork, we're going to move from 15 transactions per second to 100,000 transactions per second using the shard chain. Just a few words about sharding. Sharding is a multi-phase upgrade to improve Ethereum scalability and capacity. And the shard chains provide cheaper extra storage layers for all the application and rollups to store the data. Shard chains should ship sometimes in 2023 based on the roadmap. Improvements are related also, of course, to security with the introduction of proof of stake, moving from proof of work. And this will also introduce sustainability. We all know proof of work is quite expensive and not environment friendly. So as we just named proof of work and proof of stake, I want to give a short introduction about these two topics. So proof of work is the process of validating blocks of transactions generated in the blockchain. You might know this as mining, but the idea behind is just to build the so-called Merkle tree. So to give you some details, imagine we have 4 transactions, A, B, C, D. In order to verify this transaction and add a block to the blockchain, then the miners, so the node, need to calculate the hash of transaction A, B, and C. After that, they need to calculate the hash of the combined hash of A, B, and C and D, and then calculate the root hash, that is the hash of all the transaction combined. Now, once this hash has been calculated, the node, so the miner, will calculate the hash of the root hash, the hash of the previous block, and a nonce, that is a pseudo-random number. If this hash is valid, then it's added to the blockchain. If it's not, then the node needs to generate a new nonce. So what does it mean that the block is valid or is not valid? Well, a block is considered valid when the hash starts with a certain number of zeros that are called leading zeros that are set by the blockchain. So imagine a blockchain sets the leading zeros to 4, and the nodes are competing to generate these hashes. So the first hash, as we see in the example, is not starting with any leading zero. It doesn't have any leading zero, and it's using a nonce called A, for example. So it's not valid. The second one has 3 zeros, 3 leading zeros, so it's not valid. While the fourth one has 4 leading zeros and is the winner. So this is the block that will be added to the blockchain. What is the main difference with between proof of work and proof of stake? So in proof of stake, we do not have nodes competing to calculate the nonce to validate a block, but the validators, are selected by algorithms, pseudo-random algorithms. And it works like this. So initially, the owner stakes their tokens in a staking pool. Then the algorithm pseudo-randomly selects the next validator. And of course, the more you stake, the bigger the chance is to be selected. Then the selected validator proposes a block of transactions, and then the other validators verify and approve the transaction. And then the block is added to the existing blockchain. And then the validators, of course, earns a transaction fee. So there is no competition anymore in calculating altogether the block. But in this webinar, we're not going to go into details into attacks related to proof of work or proof of stake. We will have more from in the course. We will talk about 51% attack on proof of work, nothing at stake attacks on proof of stake, or the double spend attacks. Now I'm going to pass the mic to Stefan that will tell you more about nodes in Ethereum and especially on the Ethereum virtual machine.
Thanks, Davide, for passing on the mic to me. Yes, I'm not on mute. So in order to get to show you on how smart contracts hacking works, we'll have to cover a bit of the basis. So David explained like the basis of pretty much any blockchain nowadays, or the sort of basics of it. Now, when it comes to Ethereum, well, we should just see it as a distributed state machine. And in order for this state to be set, Ethereum has developed an Ethereum virtual machine, which is just a special kind built virtual machine that is interpreter for the assembly language that works. So the EVM, as we call it, these nodes are actually crucial to defining the rules for computing and basically defining the new state from block to block. So the EVMs, in essence, define the new state, while the Ethereum protocol itself is there to support that, right? So you have a bunch of nodes; they need to communicate somehow, and there where the protocol comes to help. The Ethereum virtual machines are a bit limited from the virtual machines that you might know. Yeah, there are limitations to it, so it cannot make like delayed calls or requests to the internet. Even though there are like over HTTPS, there are some ways how to bypass this or to overcome this through oracles. But anyways, let's not get there, or generate random numbers. Now, on the next slide, we have just another example on what that is, or what Ethereum, further explanation on what that is. And for those, well, that know opcodes, yes, so EVM is just another stack machine with a depth of 1024 items. The compiled smart contract bytecode executes as a just a set of opcodes, right? So we have the simple, well, the well-known ones that you know in any other architecture. And you have like the XOR and the add and the AND and the subtract, and the very well familiar ones. But there are also additional opcodes which make this whole thing work, such as the address, balance, and block hash, for example. So it's a virtual machine in essence, but it's specialized to support this particular case. So see it as such. Now we get to actually the smart contracts. And what are smart contracts, right? So we know what a blockchain is. Now we know now what the nodes in the blockchain are. Those are the Ethereum VMs. What are the contracts? What is a smart contract? So in essence, and the simplest way to put it, it's just code, which might sound very basic, but yes, it is. It is technically just a program that runs on the Ethereum blockchain, which is supported by the previously explained EVMs and the protocol, right? So it's a program, computer program, which is written in code, which has functions and state that identifies, addresses. These functions and state is like a, program that resides somewhere in the blockchain, and it has an address that we can identify it or call it with. Just know where it is, right? So it is important to mention, just before we continue to looking at the structure of a contract, that they're just code, they're programs. They are not, once compiled and on the blockchain, they are not controlled by the user. However, a user, as in person, can still interact with them by submitting transactions, which, as we'll see in a bit, it pretty much means calling a function in a class, right? So how do we actually write these contracts, and who can write that, and who can create these programs? Well, pretty much anyone. That's the beauty of it, right? So anyone can write that. You just need to know or get to learn how to code, learn the technology below, and write a contract in code and deploy it to the network. There are multiple languages in which you can write these smart contracts on Ethereum. We won't get into detail on the languages themselves. The most famous ones are Solidity and Viper. And today and in the training, we'll focus and we'll do it mostly or only in Solidity, because it is the most popular one, and hence why we chose it. So let's look at the structure a bit on what does a smart contract looks like. So for those that have done coding before, it will look very much similar to what they've seen as JavaScript or Java code. Some of it might, it just looks like code in any other high level programming language. So you'll see the highlighted one, the pragma keyword. You'll see it in any file, in every Solidity file. It's usually the first one, and it is used to enable certain compiler features or checks, because we write a code which needs to be compiled into bytecode into assembly that not runs on a EVM, right? So moving on, you'll see that everywhere, right? And we don't need to get into details of that now because it's not important to the example and the attack that we'll show later. So next, you can see how basically you define a contract, and that is using the contract keyword. You declare it, well, it's very much similar to classes in any other object-oriented language, as I previously mentioned. What does it contain? So it basically contains the persistence data in the state variables and functions. So variables and functions as any other code. Then, as you can see, can you go back? So variables, you define variables in a contract, so call it, i.e. the class, right? So these are called the state variables. Solidity in itself is a statically typed language, which means that each variable needs to be assigned a type, right? So it's statically typed language. Important thing to note is that there are no null values. So each and every variable that you decide is declared. If you don't assign a value, it is declared with the default value, which is representation of a 0. Now depends on the type, that changes, right? So a special one, which is also highlighted in our example, is an address one. It's basically an account. It's a hash. It comes in 2 flavors. It's a 20-byte value, which is the size of the Ethereum address, and it can be address payable when it's same as address, but it has additional members with transfer and send, because it's used for transactions. Moving on, we get to see an important thing here, which is a constructor. And for people that have written a class before in other language, this will look very much similar. So it's the function that executes upon contract creation. Before the contract code is executed, state variables are initialized, and after the contract has executed, the final code, so only after the constructor has executed, the code is stored on the blockchain. Then in the constructor, of course, we basically assign values to the variables that we've defined. So in this example here, we have the owner, which is an address type. We assign it to the creator of the contract, and we assign the cost to the value that we pass to the constructor. So that's the cost equals C. Onto functions. Functions are important. Now we said there are state variables and there are functions in a contract, right? In a class, right? So the functions are, basically the executable units of the code. They can be inside, as in this case, inside the contract, or outside. They take type parameters as input. In this case, we don't have that, but later you'll see in the actual demo of the malicious and contract, you'll see there. So it's worth mentioning that it's type parameters. There are multiple types of functions. You have the view, the pure, and each function has its own visibility. in this case here, we define this function pay as external payable, where external is the modifier that defines the visibility, which means that this function can be called via other contracts via transactions. Then lastly, what is worth noting here, you can also define view functions with public visibility. So we mentioned the visibility previously. Public means that it can be called internally or via message calls. One thing that is not on this slide, but you'll see it later, and Davide will point that out. There is also a type of function called special type of function called fallback, and each contract can have one. So we'll get to why is that important in the actual hack. Now, before we get to the hack, are there any hacks actually happening in real life? Well, as Davide also mentioned in his introduction, or the first part, there was a big hack on the decentralized autonomous organization. It happened 2016. The DAOs were built on top of blockchains. In this case, it was Ethereum, I believe, and there were some concerns right there at the time by researchers that money coins can be drained. The vulnerability was recognized, but by the time it was fixed, it was already exploited by actor and who stole funds from the DAO. Now there is some still ongoing investigation about it, or people are looking into it, and there was a recent tweet from Laura.
Laura Shane, I think, published this article where she claimed that she identified the actual attackers, and the sum material stolen would have been worth now 9 billion today. But if you want to know more about that, you can go on the Twitter profile of Laura and read the whole story. I think she published also on Forbes. So we're not gonna speculate here.
The point is, I mean, it's still happening. It's still there. It's still valid. And yes, as any other code has vulnerabilities, so do smart contracts, right? And we already established that it's just a code. Now, what was this? The actual technical issue of this hack? Well, the DAO contract was affected, or it had a re-entrance vulnerability. What does this mean? We'll explain it in the actual demo and a example, but by now you know that the Ethereum smart contracts can call each other, right? So they all live on the blockchain. They have an address, they have functions, so they can pretty much interact with each other. And we already established that these functions can be exposed, and now based on what's written in those functions and the logic behind it, these functions can be misused, can be hijacked by attackers, right? Very high level, to understand what the vulnerability is, well, it pretty much means, two contracts communicating with each other, where one is trying to withdraw balance from the other, right? So it's you can see it as 3 steps, right? So one contract initiates this by calling the function withdraw balance from my own fund, right? Then the other contract sends the fund along, of course, and passes the gas for the transactions to go through, and then simply updates the balance after. So it's simple. Give me 5. Okay, total minus 5. You have total minus 5, the new balance, right? Now, pretty simple and should work seamless. However, the technical issue on the next slide is visually represented. as a bit more detailed flow. So as we said, malicious proxy contract initiates the withdraw balance function. The withdraw balance function and the DAO contract then goes about and sends the does the transaction and sends the transfer of ether and passes along and pays the gas, right? And then the original contract, which made the call, the malicious one, has a fallback function which just triggers once again withdraw balance, right? So we never the DAO contract, if you remember the 1, 2, 3 step, so withdraw, send, update balance, we never get to the update balance part. And yeah, that's pretty much what the next slide shows as well. And as next, sorry, I didn't switch to this one, but you get the point. So initiate, withdraw, send money, can't get to update, call it again, right? Now, Davide will take over from here and show you a bit an example of how this could happen with an actual code, a smart contract that we wrote, and I believe he'll do a demo as well.
Yeah, we'll try that as well. I'm gonna take you out of screen so people can see the code.
Everyone
so in this example, we can see a vulnerable contract to a reentrancy vulnerability. So we'll go step by step into the different sections of the contract. As Stefan said, a contract is declared with the keyword contract, and then a contract has state variables. In this case, for example, we have a state variable called withdrawal limit that is set to 1 Ether. So users can only withdraw 1 Ether at a time, no more. And then we have two maps, the last withdraw time and the balances. Those are, you can think of this like hash maps. So basically an address that corresponds to an integer. And in the first map, we will store when was the last time that another contract or an address initiated a withdraw. And in the second map, there is a correspondence between an address and an integer. That is the balance of that address that is stored in the smart contract. And then we have a total balance that is the total amount of Ether that is stored in the contract. There is a function that is called deposit funds that is payable, so we can call it and at the same time send Ethereum to the contract. That the only thing that it does, it just takes the Ethereum that is sent with the call and then stores this information, this quantity, this amount in the smart contract for that specific address. And then we have the famous withdraw funds, the vulnerable function. So here we see that the withdraw funds implement some checks, security checks, we can call it like that, using the keyword require. And the withdraw is allowed for a contract or for an address only if the balance that or the amount of Ether that was stored in the contract from that address is bigger than the amount that we want to withdraw. The withdraw amount is less or equal to the withdrawal limit, so less than or equal to 1 Ether. And the last withdrawal was more than 1 day ago, so we can only pull out 1 Ether per day. And then we have the payable function, so where basically the transfer happens. So if these checks are all true, are all valid, then the contract will send the sender the amount that was requested. So again, we can only transfer 1 Ether at a time, once per day, and only if we have enough balance that was deposited already in the smart contract. If everything goes well, then the smart contract will update the balance of the user, of the address, the last withdraw time for that sender, and the total balance of the smart contract. And then there is a function get balance that is just used. It can only be used by admin. In this contract, there is no authorization. It's just a simple contract, very simple contract, just to show the vulnerability that would return the total balance in the contract. So how do we exploit a reentrancy vulnerability in the vulnerable contract? Well, we need to create a malicious contract, an attacker contract. First of all, the first thing that we need to do in our malicious contract, we need to import the vulnerable contract. Here we see it imported with the keyword import as a vulnerable.sol. This is, of course, everything is happening locally because it's a test environment, but in real life, we will import it using the address of the contract. Okay. Then we need to declare a fallback function. Stefan already mentioned it. Here we have a fallback external payable function that calls the withdraw funds of the vulnerable contract. And this is very important because the fallback functions are called when an external contract or an external address is sending Ethereum to another contract without passing any data. Okay, so in our case, we will see that the call, when the checks are true, then some Ethereum are sent to the contract, but we don't specify any data. We'll see in the next slide. And the third requirement that we have to create our malicious contract and to make this work is to add some Ether in the fund. We see here in the function attack vulnerable that is payable, we pass some Ether when we call the attack vulnerable function. We deposit 1 Ether and then we draw 1 Ether directly. Okay, so to carry on this attack, we only need 1 Ether, and the idea is to drain the whole vulnerable smart contract. So if we look at the flow, everything starts here. Once we have declared, compiled, and deployed our contract, we call the function attack vulnerable together with 1 Ether. We pass 1 Ether to the function, and the Ether is deposited, and then right away withdrawn from the vulnerable contract. So when withdraw funds is called, what happens is that the first check that requires that the balance of the sender is bigger than the amount that we want to withdraw passes, because we deposited 1 Ether and now we have 1 Ether and we want to withdraw 1 Ether. So this check is true. The next check, we have that we remember that the withdrawal limit is 1 Ether. So also this check is true because we are requesting 1 Ether. And then because this is our first transfer, we never transferred before. So also the third check is true. And then our function that the function that sends us Ethereum from the vulnerable contract to the attacking contract is called. And here we see that no data here. There is nothing that is passed to this function, but we call the contract directly. We're just sending Ethereum to the contract. And when this happens, then the fallback function is called. And when the fallback function is called, then the withdraw funds again is called. And reiterating again and again and again the withdraw function, the call of the withdraw function, while this block here, the success true block, is never executed till the vulnerable smart contract is empty, pretty much. But we can see it in a quick demo. So I will just bring the slides away and bring that we saw. Whoop. Yeah, that's better. Our vulnerable contract is exactly the same, what we just said. We have our fallback function. We have a receive function just to please the compiler. And we have contract. Okay, so this is the vulnerable. We compile it. And then, of course, we can choose a different virtual machine. Here we have some addresses that we can use to deploy the contract, to transfer Ether. And we deploy both contracts. We already deployed the vulnerable contracts. We see here the functions. We see deposit funds is red because it's payable. It's possible to transfer functions. If we click get balance, we see that the contract is empty, 0. And now we're gonna transfer some funds to the vulnerable contract. Imagine this is the DAO contract. See, we transfer 5 Ether, we take another address, maybe a friend of the other address saying like, this is a cool contract, transfer other 3. with deposit. So now the get balance should show 8. Now, let's take this address as an attacker. We deploy the attack contract. In order to deploy the attack contract, we need to specify the address of the vulnerable contract because we want to import it. We see that the deployment is successful in Remix. And now, in order to carry on the attack, we just need to call the attack vulnerable function. We just have some cool functions here. Admin will show us the admin address, and we see that the balance in this attacking contract is 0. So this is the address of the attacker and the admin of the malicious contract. And again, we transfer 1 ether, remember, because we have it as a requirement. And now we see that the call of attack vulnerable was successful. And if we do get balance, then we see that the amount of money that is in the contract is 9. So this is just an example of the vulnerabilities that we have in the training. The training is inspired, I would say, by the SWC registry, the Smart Contract Weakness Registry. It's a very nice registry like the CWE for web application, for example, where there is a list of vulnerabilities inspired by the latest hacks. So I'm gonna bring back Stefan as well to the stage. So what's in the training that we published last month? Well, the SSCH is 1.5 day hands-on learning plus half day of pure hacking, where we will give to the students vulnerable smart contracts to deploy, to hack, to attack, but also to defend. And at the end of the training, there will be a certificate completion for the students. You can see the full program on the link. We will put the link in the chat as well. So
I'm not able to send links to the chat though. So David, if you can do it, please.
I will do that. Yeah, I will do that in a bit. So the modules of the training start. Of course, everything starts from an introduction on Ethereum and smart contracts, and then we have 2 parts on smart contracts. We will deep dive into how smart contracts are built, what are the keywords, difference, how to use smart contracts to call functions, how to declare functions in different way, how to implement authorization. So also, if you are not really familiar with smart contracts or you are just starting with smart contracts, no worries at all, because we're gonna build a smart contract from scratch. Of course, we are not gonna spend 2 days only on what a smart contract is and Solidity, but there is a big part on that. And then we will go into how to implement authorization, for example, using the Open Zeppelin smart contracts, denial of service attacks, all the SWC vulnerabilities that we just saw, and how to carry security auditing on smart contract. And then we will have the final half day where we're gonna hack a bunch of smart contracts that we'll deploy. So when is the first session? The first session is scheduled for the 23rd of June, 2022. And we have a cool discount that we're launching today. We launched it already last month, but we want to share it with you. And if you use the coupon SSCH beta 22, you will have a discount of 350 euros. So the final price will be only 150 euros, if I remember correctly. I will share the link also in the chat to book the training in a bit. But if you have more questions, of course, the coupon and all the information will be available in the recording. We will publish the recording of this webinar on our YouTube channel, on LinkedIn, on Twitter, so you will see it everywhere. And if you have more questions, of course, you can reach us out via Twitter, LinkedIn, or via email, or WhatsApp as well. So I will just remove the slides. And Stefan, thanks for putting the coupon on screen. And well, the webinar ends here. Of course, we will respond to all the questions after the webinar. And again, reach out for if you have any tips, questions, or just to have a coffee or a chat. Thank you.
Thanks all. I see some familiar faces in the chat as well. So definitely, and I haven't seen some of you in a while. So do reach out for a coffee.
Bye-bye.
Strange. Okay. Thanks a lot, Davide.
Thank you, Stefan. See you
Thank
later.
you.